Prosthetics today are extremely expensive. They can cost anywhere from $10,000 to $100,000 and are extremely difficult to use. The WHO has estimated that 150 million people globally don't have access to prosthetic devices for these reasons. To improve prosthetics, I worked with a professor and master's student at San Jose State University to develop a vision-based control framework which formulates robotic manipulation as an MDP and learns grasping using DDPG. This automates the process of identifying, grasping, and interacting with objects for amputees, making the arm much more personalized based on the user's behavior and interactions, and easy to use. We also developed a new 3D printed material and design that is able to reduce the cost from $10,000 on average to just $700, making the arms much more accessible to people globally. As well, I wanted to thank the developers at Maya, as well as researchers at the Blink Lab who supported me a ton on developing this work. This is what our final prototype looks like. We have the Jetson Nano that takes care of the object detection and the Arduino Nano for controlling the prosthetic arm. I'll be speaking more about the vision-based control framework and how this works, but before I get into this, I wanted to show a quick demo of what our prosthetic arm looks like. So here you can see the fingers actually closing and forming different grasps. Current prosthetics are controlled directly via a user's myoelectric signals. So these are electrical activity from the muscles that are recorded from the skin surface of the stump. A myoelectric band is used to capture myoelectric signals and then understand the user's intention. This, alongside the camera on the prosthetic, is used to capture an image of the objects in the environment and process these by extracting key features such as what objects are in view. These images are sent through a vision-based control framework that we've designed, which is based on a general formulation of a robotic manipulation as an MDP to make prediction for the best grasp to grab that object. The identified grasp and myoelectric signals are then sent through the prosthetic controller for proportional control. Our vision-based control framework is based on a general formulation of robotic manipulation as an MDP. The policy observes the image from the robot's camera and chooses a gripper command. An MDP consists of actions, states, and a reward function. We factor the Q function into several independent convolutional neural networks, or CNNs, one for each time step. To capture images, we mount to the camera on top of the actual prosthetic hand. To define the state, we set a pick place task as k equals 2, since there's really only 2 observations which are present: the target of the grasp or place and what the hand actually contains. The agent's action comprises of a gripper pose displacement, which is the difference between the current pose and the desired pose in Cartesian space, and an open/close command. The grasping task is defined simply by providing a reward to the learner during data collection. A successful grasp results in a reward of 1, and a failed grasp in a reward of 0. In order to detect a successful grasp, an image subtraction test is used. 2 images are captured, so an image of the scene after the grasp attempt, and then another second image is taken after attempting to drop the grasp object. If no object was grasped, these 2 images would be identical. Otherwise, if an object was picked up, certain pixels in the 2 images will be different. We train the off-policy method of deep deterministic policy gradient, DDPG, for learning of this task. DDPG combines elements of Q learning and policy gradients. It aims to learn a deterministic policy by propagating gradients through a critic. The actor is trained in DDPG according to the objective, which is an approximate maximizer of the Q function with respect to the action at any given state S. Right here is a demonstration of the grasp being conducted during the learning on a simulated model of the anthropomorphic hand used as part of the Southampton Hand Assessment Procedure, or SHAP. We built a data set, and this was built on top of the Cornell grasping data set that's open source. The Cornell grasping data set contains 885 RGBD images of real objects with labeled positive and negative grasps. This data set is effective as multiple labeled grasps are provided per image for various different objects. We augmented the Cornell grasping data set with random crop, zoom, and rotations to create a greater set of over 140K depth images. We found this approach to be effective in generalizing across multiple everyday objects such as cuboid, sphere, cylinder, can, and screwdriver. We were able to achieve a 78% grasp success rate on previously unseen objects and 84% on household objects that are moved during the grasp attempt.